Today we're going to talk about transformation of graph by shrinking and stretching. In this case, we're going to talk about what if you multiply a number inside a function or outside a function. Last time we discussed adding or subtracting values to the x inside or outside, which caused the vertical and horizontal shift. Now, let's say you're given a function f of x, and now instead of f of x, you have f of ax. That means x has been rescaled by some constant a. A is a real value. It could be positive number, negative number. Let's assume it is positive for simplicity. Later on, we will discuss negative values. If that happens, remember if we added a number inside a function, it caused the horizontal shift in the opposite direction. So if we multiply a number, what it causes is it affects the x value, but in the opposite order. So if you multiply a number, all the x values will get divided by that specific constant. So if the number is like 2, if you have f of 2x, then all the x values will divide by 2. If you divide a number by, if you multiply something like 1/2 times x, then the numbers will get rescaled. So instead of, if let's say you had f of 2x, then all the x values will divide by 2. But if it was f of 1/2 x, then what happens, all the x values divide by 1/2 means all the x values will multiply by 2. So a rescaling will happen in the opposite order. What if you do it outside? If you multiply a constant to the f of x, that means all the y values are going to change. All the y values will rescale by a. If a is greater than 1, so it will be stretching. If a is smaller than 1, it's shrinking. So the stretch and shrink basically depends on the scale that you're multiplying. If a is bigger than 1, you're stretching the graph. If it's smaller, then you're shrinking the graph. I'll do examples just to show you. So here's a example. F of x is given square root of x. We already know how the square root of x looks like. Here, square root of x, something like that. And you can pick a couple of points. 0, 0 is there. 1 and 1. Here's 1. And then we have 4 and 2. Let's assume this is 2. That's the other point. I picked 3 points, for example. So this is square root of x. Y equal to square root of x. How about the g function? The square root of 2x. What happens is, if you compare g and f, you've changed inside the function. Instead of x, now you have 2x. So you rescale the function by saying that gx is basically f of 2x. Instead of x, we replace 2x into the function f. So what is the relation? The relation is that all the x values now get divided by 2. The y values do not change. All the x values will divide by 2. So there is a shrink. Every x value will divide by 2. So what happens to the graph? I'm not going to change any y value. The x value of 0 divided by 2 is going to be still at 0. X value of 1 divided by 2 would be at 1/2. You can say 0.5 or 1/2. X value of 4 divided by 2 will give you a 2. How about the y values? The y values are going to stay the same. 1 is going to be the same. 2 is going to be there as well. So here, 1 and 2. And then now draw a curve through these points. So what we did is we shrink the graph in this direction along the x by dividing all the x values. You didn't change any of the y values. You just shrank the graph along the x direction. Because the coefficient here was bigger than 1. It was 2, so the graph shrank. And again, this is not super complicated. You can use a different method. You can draw the table and say, I want to graph it using the table. I'll pick 0, I'll pick 1/2, I'll pick 2. If you do this and use the f of x equal to the square root of 2x, what you get is the y values are 0, 1, and 2 precisely, which are going to be exactly these points. Then draw a curve through those. But based on the idea of transformation, you can do this as well. Start with a simple function f, then you can generate the function g as well as the function h. Now, how do we graph the function h? Function h is an example of, so here h of x, which was 3 square root of x. This is the same as saying 3 times f of x, because f of x is just square root of x. So we've rescaled the function f by 3. How did we do it? We multiply the function by 3. So that means all the y values get to multiply times by 3. Get to multiply by 3. This is the stretching case along the y direction. So what do? Consider the graph of square root of x. I'm not going to change any of the x values. The x values stay fixed, 0, 1, and 4. What happens to the y values? The y value gets stretched. So 1 multiplied by 3 becomes 3. 2 multiplied by 3 becomes 6. So the points that you had, 1 and 1 becomes 1 and 3, and 4 and 6. So the curve basically looks like something like that. So it's a stretch along the y direction if you multiply a constant outside. And you can draw this table. It's not necessary, but you can do it. You can say, I don't want to go through the square root of x. I can just pick numbers. Say 0, 1, and 4. What do I get if you replace it into the function h? So if you look at the function h of x, which was 3 square root of x, if I replace 0, what do I get is 0. If you replace 1, what do you get is 3 times square root of 1, simply 3. If you replace 4, 3 times square root of 4, which is 3 times 2, you'll get 6. So what are the points? 0, 0, 1, 3, and 4, 6. You can graph the function through those points. Okay, so it's not necessary just to use transformation, but sometimes you're not given the function equation. So what you're given is just the graph and say rescale it. How you rescale it is just based on this idea. Okay. So far I'm not going to do any negative because the negative number rescaling causes a reflection. I'm going to do it in the next topics as we go on. So this was an example of stretching and shrinking. By the way, here let me show you if the number is smaller. So let's say we still know the square root. What if they give you k of x and they say k of x equals square root of 1/2 x? And what does this function looks like? This is the same as saying f of 1/2 x, because f of x was square root of x. I'm using the same example that we did already. So instead of x, if you replace 1/2 x, what do you get is the k function. The k function is basically f of 1/2 x. So what is happening here is all the x values have changed to 1/2 x. That means all the x values should be divided by 1/2. Or if you simplify that, divide by 1/2 is saying x multiplied by the reciprocal of 1/2 is 2/1. So all the x values are getting multiplied by 2. So what happens, instead of shrinking, now you're stretching the graph along the x-axis. All the y values, still fixed y values, which were 0, 1, and 2. 1 and 2. X values, instead of being 1 and 4, they rescale. 0 times 2 becomes 0. 0 is still there. 1 times 2 turns out to be 2. 4 times 2 becomes 8. So all the points are going to scale along the x-axis. The graph will look like it's a curve, but my rescaling is not that well, so you should consider that the graph is curved. So this graph, the square root, will stretch along the x direction. The same for y, you can create the same example. Okay. Here we go through transformation of quadratic, cubic, square root, and absolute value function. These are the specific functions that we want to discuss. But before we do that, maybe we should mention how do they look like. I'm going to graph each one separately. So quadratic function, we've already discussed a specific case, ax squared plus b. We discussed the vertex of the quadratic and so on. So let's assume we only discuss in this case the simplest case, x squared. And I mentioned that the graph of x squared looks like that. So what if there was a plus 3? You remember from last time, then that plus 3 outside will cause the vertical shift. So the graph will go up 3 units. What if there was x plus 1 squared? Then what happens is this is a horizontal shift to the left 1 unit. You move the graph 1 unit to the right, to the left. What if the graph, the function instead of that was 3x squared? This causes a rescaling, a stretch or shrink. But since it's a coefficient of the function, so this is a y multiplied by 3. All the y values get multiplied by 3. What if the graph was 3x, the whole thing squared? Now it's a change inside the function. So what does it mean? It means all the x values get to divide by 3. So if you know the graph of x squared, you should be able to create any type of other function and how the transformation affect them. So first, let's assume we know the x squared. How does it look like? And similar ideas hold for cubic and square roots and absolute value function. So first, absolute value of x. This is absolute value of x. Here, let's draw the other one as well. I've mentioned the square root just now. This was the square root. This is a vertex point. Cubic function, we haven't discussed it. So what does the cubic function look like? F of x equals x cubed. And there is a cube root as well. Let's do them separately. Let's say I'm going to use the color black for cube root of x. And x cube, I'm going to use green. You can pick points to graph it. But cube function looks like this. X cube. This is how x cube looks like. If you replace 0, y value becomes 0. If you replace 1, you will get 1. If you replace -1, you'll get -1. If you replace 2, what do you get is 8. 2 cube is 8. If you replace -2, you'll get -8, and so on. So you can pick a couple of points just to graph the function. And you will see that you create this shape. How does this cube root of x looks like? It would look exactly the same thing, but flipped around the other direction. So it's going to be symmetric the other way. Because these are inverses of each other, which is a kind of reflection. We're going to discuss that later as well. So if you want to graph cube root of x, you can pick these points, 1, 8. You can pick 0, -1, -8 for simplicity. You find y values of -1 and -2. You'll find y values on the other side, 1 and 2. If I pick 8 and 1, sorry, it's the same point. Okay, so the shape is what matters. Calculation, you can always do it. So here, let's do an example of the transformation of maybe a couple of these guys. Here's the example. Let's say f of x is given something like 2 x minus 1 squared plus, let me say, let me change this actually to a different number. Let me make this 2 1/2. Or why not? Let's keep it as 2. Why not? Plus 1. I don't want the numbers get too so large, but that's okay. So here is an example of transformation that you can combine the information that you have learned. Okay, if you start with a simple function f of x equal to x squared, what changes do you make to get to this function? That's what we're going to go through. First change that you have to make is instead of x, you should have x minus 1 squared. So the first function that you will get is x minus 1 squared. This is the first change. And what does that change do? It affects the graph in a way. It would be a horizontal shift. How many units? 1 unit. In what direction? In the opposite direction, to the right, because you have -1. Okay. What would be the next change? After I got this graph, I have to rescale it by 2. 2 times x minus 1 squared. So I'll multiply a 2 to the function. What happens? That causes a stretch or shrink. In this case, it's a stretch. How does it stretch? It multiplies all the y values. It multiplied by 2 by this coefficient, since it's outside the function. What's the last step to get to the final function? We add a 1 at the end. So what does that one do? It's a vertical shift. How many units? It is 1 unit upward. So if you combine all these 3 steps back to back, if you start from the graph of x squared, then do a horizontal shift 1 unit to the right, then rescale all the y values by 2, then vertical shifted up 1 unit. What do you get at the end is the graph of f of x. 2x minus 1 squared plus 1. This is what you will get. So I'm going to draw that. I'm going to use different colors at every step, so you can keep on with the same pace. You can draw them in different on different rectangular coordinate system every time and update. So here, let's start with the first step. Step one, I will have the x squared function. This is the x squared function. You can always pick a couple of points on the x squared function. 0, 0, 1, 1. And figure out where these points will end up. And on the other side, you should have -1 and 1. This is 1. You can pick another point if you want. 2 and 4 is always there as well. This is for the x squared function. Okay. Then what happens in the next step? I'm going to use step 2. The first step would be do a horizontal shift 1 unit to the right. So this point will move here. Next point on the graph, this point will move 1 unit to the right. The left point moves 1 unit to the right as well. So what happens to the graph? The graph totally will shift 1 unit to the right, every point. I'm moving every point to the right. This is the graph of x minus 1 squared. Okay. Next step, if I rescale all the y values by 2, step 2, since there is a stretch, and multiply all the y values by 2. Instead of y value of 0, 0 times 2 still stays there. X values do not change. The x value 2 is still there. The y value, instead of being 1, now gets rescaled to 2. So this point will get to here, as well as this point will move up. So what you do is all the y values get rescaled by 2. So what you do is you stretch the graph along the y direction by 2. This would be the next step. And now finally, at the end, what you have is the graph of f of x if you vertically shift the graph up 1 unit. So every point now from the blue graph, if you shift every point 1 unit up, this would be the next point. Here would be the other points. And what you get is this black graph. You should do it precisely by picking a bunch of points and go through those points, rescaling, moving up and down. But I want you to see how the steps are constructed. So this black graph at the end is the graph of f of x. Again, you can always pick points and figure out exactly. If I ask you where is that vertex point, if you remember from last time, inside this must be 0, so you'll get x equal to 1. You replace 1 into the function, what do you get is y value 1. So it is exactly at 1 and 1. And you'll see that that is correct. Okay, here, let's try another one. Here's another example. given f of x as I don't know, how about if we do 1/2 times, maybe we should do 1/2 x, absolute value of 1/2 x, then minus 1, something like this. Okay, and we try to graph f of x. Graph f of x by transformation. You can always graph it by picking point. This is what we're trying to do in all this section. So what do? We start with a simple function. What is the simplest possible function? What we know is f of x equals square absolute value of x. Sorry, not f of x, because I already have the f of x. I'm going to call it y. I'm going to start with the simplest function, absolute value of x. I know how the graph of that looks like. Then after that, I'm going to build the function f through the process. What do you do? The first step is you have to figure out where do you get this 1/2 x. Then the next step would be, how do you get to 1/2 x minus 1? At every step, there is a transformation. From absolute value of x to 1/2 to absolute value of 1/2 x, what happens? It's all the x's get multiplied by 2, or you can say it's divided by 1/2, which is exactly what we did last time, and say this means all the x's get to multiply by the reciprocal of 1/2, which is multiplied by 2. This is what it means. X divided by 1/2 is the same as all the x's multiplied by 2. These two have the same meaning. Okay, so this is what is it? This is a horizontal stretch. Because you're not changing the y values, you're changing the x values. Every x value gets rescaled. And finally, if you subtract 1, this is a vertical shift 1 unit down. Okay, I'm gonna graph this by doing it. You can do it this way. I'm gonna do it separately so you can see. Absolute value of x, how does it look like? This graph. Then what was the next step? Step 2. Step 2 was to figure out what is y equal to absolute value of 1/2 x looks like. So for that, I'm going to pick a couple of points on the graph. I have 0, 0. I have 1, 1. 2, 2. You can say -1 and 1. And -2 and 2. You don't need to pick 20 points, just picking a couple is enough. In this case, picking actually 3 points is good enough. So what happens? All the x's will get multiplied by 2. The y values do not change. Still, you would have 1, 2, and 0. The x, 0 multiplied by 2, still at 0. 1 multiplied by 2 becomes 2. There's a point 2 and 1 now is there. The y value did not change. The y value is still 1 and 2. 1 and 2. But the x's will be rescaled. 2 multiplied by 2 becomes 4 here. And on the other side, you would get -2 and -4. I'm multiplying all the x values by 2. How does the graph look like? It's this straight line passing through these points. What happened to the graph? We stretched the graph along the x-axis in this direction. You're pulling the graph in the x direction to stretch it. And finally, if you want to graph f, which is a combination of all these, absolute value of 1/2 x minus 1. This is a vertical shift down. So shift the graph down 1 unit. Every points will shift down 1 unit. So this is 2, 4, -2, -4. The y values shifted down. Instead of being at 1, these two will become 0. The other side, instead of being 4 and 2, it becomes 4 and 1. There's 1, -4 and 1. And the vertex moves down 1 unit, becomes at -1. So the graph is now like that. Okay, so now I have the graph of absolute value of 1/2 x minus 1. Again, you could graph this always by doing finding the vertex point and picking a couple of points, but this is the idea of the transformation. We're using the transformation. Okay, now one more topic in the transformation is, so far we haven't talked about multiplying a negative number. What happens if you multiply a negative number? Well, that causes something called reflection. So if you multiply a negative number inside the function, it causes a reflection. And how does it affect the function? All the x's will change from positive. If you pick a number here, all the x's will change from being positive to negative. If you change x to negative x, if you have a 3, change it to -3, it'll go there. If you pick 4, multiplied by a negative number, we'll move to the other side. If you have a graph on the right side, what happens to the graph I'm multiplying? It will be exactly the same graph on the left side. So if you multiply a negative number inside, you're causing the reflection of the graph about the y-axis. So the graph would reflect along the y-axis. What if you multiply a negative outside the function? All the y values that were like positive, if the y value was 3, if you multiply a negative to it, it becomes down here, it becomes -3. So that point moves down here. If they have a +2 as a y value, moves down here. All the y values turn to from positive to negative or from negative to positive. So if you multiply a negative number outside, it causes a reflection about the x-axis. This is the only two cases. Either you cause a reflection about the x-axis or about the y-axis, depending on where you multiply the negative sign. Here's a good example. If you have f of x equal to negative square root of x, and you want to graph this through the square root of x function. Since you already know how the graph of square root of x looks like, this is the graph of square root of x. So how would f of x looks like? F of x is negative times square root of x. That negative is multiplied outside. So multiply outside means reflection about the y-axis. So this would be the graph of negative root x. You reflect all the points. The point 0, 0 reflected about the y-axis is still there. But the point 1 and 1, if you replace 1 into the f, what you get is -1 for y value. That's why you will have a reflection now. If you pick point 4 and 2, you replace 4 into the function f, what you get is 4 and -2. All the y values will reflect. And on the other side, if you want to graph the function h of x, which is negative square root of negative x, it's a reflection of all the x's along the y-axis. So you graph the square root of x reflected along the other one. So this is square root of negative x. And if you look at the domain would be only a negative number. Because if you replace a negative number in here, negative times negative becomes positive. That's why the domain has changed from positive to negative section. And there's a combination of both of them. If you have negative square root of negative, that means you reflect both direction. And what you end up with is basically this graph. This is negative square root of negative x. Okay. I'll do an example containing all these together. This is if you multiply a negative number. So here is the issue. If you have the graph, the equation of the function, you always can do this. You can pick the numbers and figure out what the function looks like exactly. But sometimes they give you a graph. Here's an example of that. You're given y equals f of x. How does f of x looks like? They give you the graph of it. They don't give you the equation. They tell you this is this point. Here's a point, straight line, and then another straight line. And let's assume this is -2, this is -1, this is at -1, and here's 3. Okay, and this one is 2, this height. And they ask you to graph this function, graph the new function. What is the new function? The new function is -2 f of x plus 1 plus 2. So I'm going to break it down. If I start from the f of x function, what would be the first transformation? The first transformation is this change of x plus 1. So what happens? You will have a horizontal shift. How many units? 1 unit. In which direction? In the opposite direction. So to the left. Okay. Then I'm going to look at outside because I've dealt with the inside part. This 2 outside. The 2 will tell you is there is a stretch. Sorry. Yeah. Stretch. Maybe I should have said. What does the 2 means? It means all the y values get to multiply by 2. That means you will have a vertical stretch. All the y values get vertical stretch. All the y values get multiplied by 2. Then after that, you can deal with the negative sign. You can combine the -2 actually and say all the y values get multiplied by -2. That's one way to do it. But I'm going to break it down so I've discussed the reflection as well. This negative number outside means negative f of x, as we discussed here above. You multiply a negative outside the function. It's a reflection about the x-axis. So the third step would be to reflect about the x-axis, because you want to change all the y values from positive to negative or from negative to positive. And finally, the +2 at the end, that would be the fourth transformation. This is a vertical shift. How many units? 2 units. Which direction? Upward. It's only the changes inside that are going in the opposite direction. Any change outside always follows the same. If you have a +2, it's positive going up. If it's -2, you'll shift it down. Okay, now starting with this graph, you can always pick a couple of points to follow them to see what happens. I'm going to pick these 4 points to see what happens through the procedure. Okay, here, let me write the coordinates. The given points are -2 and 0. This is one of the points. The other point is -1 and 2. Here is -1 and 2. Then I have 0 and 2. Erase that. 0 and 2. And then the other point is 3 and 0. What I'm going to do is, this is starting from the graph F. I'm going to follow the transformation and say, through the first transformation, what happens to these points? There's a horizontal shift 1 unit to the left. That means all the x's move 1 unit to the left. From -2, you'll get -3. The y value does not change. I have -2 and 2. 0 moves to -1. Again, y values do not change. You're subtracting 1 from every x value. So 0. Okay. So what does the second step do? Tells you that all the y values now get to multiply by 2. I'm going to multiply every y value by 2. The x's do not change. 0 times 2, still 0. -2 and 2 times 2 becomes 4. -1, 2 times 2, 4 again. And here 2, 0 times 2, still 0. I'm multiplying all the y values by 2. Final third step. Reflect about the x-axis. Reflect about the x-axis means change here y from positive to negative, and if y is negative, to positive. You're reflecting, you're picking a point from top, moving to bottom, from bottom to top, if there is such a case. You're changing all the y's from positive to negative and negative to positive. So what happens to this case? 0 is still at 0. -2, 4 becomes -4. I'm multiplying all the y values by a negative number. -1, actually. You can combine step 2 and 3 together and do it at the same time, but just for the idea, I'm gonna break them up. Finally, step 4, vertical shift down 2 unit. Vertical shift does not affect the x values, it's the y values that are moving up 2 unit. So 0 plus 2 gives you 2. -4 plus 2 gives you -2. Again, -4 plus 2, -2. And 0 plus 2, y value becomes 2. So I did all these, and now I have 4 new points. Find those 4 points, -3 and 2. -3 and 2. Then I have -2 and -2, -2 and -2. Then you'll have the point -1 and 2, -1 and 2, and 2 and 2. 2 and 2 somewhere here. Okay. And if you remember the shape of the graph, there is a straight line, then a horizontal line, then another straight line connecting these points. And if you compare the two graphs, maybe I can pick this and move it down here. Maybe I can do this. Now, if you compare these two graphs, what happens is you have effectively have created those process. You've picked these specific 4 points. You've picked these 4 points, and you followed them through the process. Every other point that you pick along this line is going to follow the same procedure, and you'll end up exactly along this line. But since we do not have the exact coordinates, it's good enough just to use these 4 points, because they create the structure of the graph. So what did you create at the end is this new graph of -2f of x plus 1 minus plus 2. This is what you got. You shifted the graph 1 unit to the left, then you rescaled it by 2, reflected by a negative, then you moved it up again 2 unit. And at the end, what we got is this graph. And this is what basically we're looking for. I hope it is clear, the procedure. And every other graph you always see is just you have to break it up into these processes. What do the transformation do? Okay, I'm gonna stop here.